Hey everyone, welcome back to Logical Thinking, and in this video I'm going to talk about the contrapositive. So I'll tell you what it is and why it's equivalent to the conditional. I'll actually prove that it's logically equivalent to the conditional in this video. So to understand the contrapositive, let's look at our conditional that we're all familiar with. P implies Q, or if P then Q. We're going to define the contrapositive as if not Q then not P, or not Q implies not P. So as an example, let P be the proposition that my PS5 is in my living room, and Q be the proposition that nobody stole my PS5. Now you may look at this proposition and say, hey, it looks kind of like a negated proposition. Yeah, that's fine. It actually doesn't matter. Once again, we're looking at the form P implies Q and not Q implies not P. So that proposition may itself be a conjunction, or it may be a part of another proposition. That doesn't matter. What matters is the relationship between P and Q. So if I say P implies Q, what that's saying is if my PS5 is in my living room, then nobody stole it. And what the contrapositive is saying is kind of the opposite. If somebody stole my PS5, once again, negating Q, so if nobody stole my PS5, then somebody stole my PS5. So if somebody stole my PS5, then it is not in my living room. So what we're going to be showing is that P implies Q is logically equivalent to not Q implies not P. But before we do that, let me show you how this is related to modus tollens. So remember, with modus tollens, we have P implies Q, premise 1. Premise 2 tells us not Q, and therefore we conclude not P. So what modus tollens basically tells us is if P would imply something is false that we know or assume is true, then P must also be false. So it's kind of like looking at it backwards a little bit. So this is like saying, look, if my PS5 is in my living room, nobody stole it. Somebody stole my PS5, and therefore my PS5 is not in my living room. It's kind of like reasoning from the negated conclusion back to a negated premise. But consider this another way. Suppose I started with premise 1, which was the contrapositive we've been talking about. Not Q implies not P, not Q, therefore not P. This would be like saying, if someone stole my PS5, it won't be in my living room. Somebody stole my PS5, and therefore my PS5 is not in my living room. And what this shows is that modus tollens, where you take modus tollens and you swap out premise 1 for the contrapositive, actually becomes modus ponens. It just becomes modus ponens with negated premises. So this is one reason to think that these are two ways of looking at the same thing. If you take modus tollens and you replace premise 1 with the contrapositive, which we're going to show is logically equivalent, which means you can do that, then you get basically something of the form modus ponens. So what that also shows is that modus ponens and modus tollens are basically the same thing as well. So let's go ahead and do this. Let's go ahead and show P implies Q is logically equivalent to not Q implies not P. Now, one way we could do this is, as we've been doing it, is showing it with the truth table, but I actually want to do it a little bit differently. And by doing it differently, we're going to introduce something that will be helpful to you as you continue doing these kinds of arguments. So as a corollary, meaning off to the side, we're going to prove something else. I want to prove that P implies Q is logically equivalent to not P or Q. So let's go ahead and show this. And kind of the intuition before we get started is remember that P implies Q is true everywhere except the antecedent P is true and Q is false. So P implies Q is kind of equivalent to not quantity P and not Q. And if we apply De Morgan's law to not quantity P and not Q, remember we distribute that negation and we flip the conjunction to a disjunction. So we'll get not P or Q. So here we go. Once again, we flip the sign, we distribute the negation, we get double negation on Q, which is just Q, and we get not P or Q. Another way to show that this is the case is to look at the truth table. So if I put P, Q, P implies Q, and not P or Q, we know P implies Q. We've done this a bunch of times, so I'm not going to go through it again. It's true everywhere except where the antecedent P is true and the consequent Q is false. So it's true everywhere except that second row where it's false. And let's go ahead and do this disjunction here on the right. So let's first fill out the values for Q. It's true in lines 1 and 3. And remember, our disjunction is true if either one of them or both are true. So we can actually go ahead and put true in lines 1 and 3 because we've already met that condition. And let's go ahead and look at not P. So we have P. So we want to look where P is false. Where P is false, then the disjunction is actually true. So that's going to be those last two rows of the truth table. We're going to put a true there because once again, either one of the arguments or both has to be true for that disjunction to be true. And it's false when both are false, which is that second row that we have. And sure enough, when you look at this, at these two columns in the truth table, you'll see that they're both logically equivalent. Of course, as we talked about, you can show two things are logically equivalent to show that they have the same truth value in every model, which means just comparing their columns in a truth table is one way to do that. And therefore, we've shown that P implies Q is logically equivalent to not P or Q. So now let's go ahead and show that P implies Q is logically equivalent to not Q implies not P. So what we're going to do first is we're going to write P implies Q as not P or Q. This is what we just showed from our corollary. And what we're going to do now is notice that our disjunction is commutative. We can basically swap the order of it. You can't swap the order of the conditional. Once again, that creates the fallacy of affirming the consequent, but you can flip the disjunction, the order of the disjunction. So not P or Q is logically equivalent to Q or not P. In general, A or B is logically equivalent to B or A. And you can show this is true with the truth table. And let's go ahead and write Q or P as not quantity, not Q, or not P. So what I'm kind of doing is grouping things. Remember, a variable is equal to its double negation. We showed this was logically equivalent via truth table in a previous video, so we can go ahead and use that result. And kind of as an aside, that's one of the cool things about this. You're going to build up this toolbox of things you've shown, and then you can just kind of substitute those in whenever you want to. It helps you kind of be lazy. So that's what we're doing. We're going to use that fact that we showed before and just introduce a negated Q. And what I'm going to do here is be a little bit tricky. I'm going to define a variable x as not Q and define a variable y as not P. So what we're going to actually have is this is going to be not x or y. So Q or not P is logically equivalent to not x or y. I've just basically defined these kind of dummy variables. And now we're going to use our corollary again. Since not x or y is logically equivalent to x implies y, we can then conclude by substituting in not Q and not P for x and y, we'll have our result as desired. So this once again comes from our corollary. We're just using it again. We can conclude that Q or not P is logically equivalent to not Q implies not P, and thus we have gotten to our answer. We have shown that if we start with P implies Q, by doing all of these steps that are all logically equivalent, we get something that is of the form not Q implies not P. So our proof showed the if and only if direction. It showed logical equivalence because we started with one form and showed how it is logically equivalent to the other. So every step in this proof used logical equivalence. So this isn't just a one way. We actually showed the if and only if case. And this is one way you can do those show A if and only if B proofs. Sometimes you'll get a proof and it'll say show A if and only if B. And what you have to do is show that A implies B and show that B implies A. But if you can show that A is logically equivalent to B, meaning you start with A and all of your steps are proving logical equivalence and then you get to B, then you're good. You basically have shown the if and only if case. So what we've done is showed that P implies Q is logically equivalent to not Q implies not P. In other words, P implies Q is true if and only if the contrapositive not Q implies not P is true. And sometimes when proving things, that contrapositive is going to be easier to work with. So consider you have something that says, look, prove that if A, then B. You can prove this by showing A implies B. This is a direct proof. Or you can use the contrapositive because once again, if A then B is logically equivalent to if not B then not A, you can prove the same thing by showing not B implies not A. So really it comes down to choosing the one that's easiest for you, and sometimes one works a little bit better. Now, one thing I'll note is in mathematics, often a constructive proof is considered better because it may show or use some hidden relationship between the two propositions that a contrapositive does not. However, logically speaking, both are equally valid. So even if, people may prefer one over the other because maybe they think in general it gives more insight, that doesn't mean logically one is somehow better than the other. They're both equally valid, if you will. So anyway, thanks for watching. Hopefully you found this helpful. And in the next video, I'll show how we can use the contrapositive to do a proof by contradiction.